Okay, so again, good morning, good evening, and good day to everyone. So the paper that I'm going to talk about, it's a very recent paper. Thanks to Sam uh, and the other people for allowing me to present this paper. It's called Natural Adversarial Objects. Right? The paper was released only this November, and in this particular paper, most of the papers that we have encountered till now, most of the cases, what we are looking at are probably some new methods, some new models, which can probably uh, help us get better results from machine learning models and things like that. But not too many studies have been done whereby the objective of the study itself give rise to newer data sets or trainings with which the models itself could be trained. Just think about it. You are as good as the training that you have received, which means that if the training which has gone into you, there was some kind of a fault in that, there was some lacuna in that, your learning, your training will not get completed. So whenever we talk about machine learning, deep learning models, make no mistake, these models are as good as the data on which they were trained. So if there were biases in the data, if there were lacuna in the data, obviously the model will also behave like that. So in this particular paper or in this particular work, what they have tried to show is that many of the state-of-the-art object detection methods, where we are saying that, okay, the performance is actually very great. So in those cases, the training data which they had were probably pretty much simple, straightforward, right? And sometimes not coming with too much of a complexity or challenges or surprises. What will happen if the training data itself is presented has a lot of surprise elements in that, a lot of challenges in that? That's what we are going to study in this particular paper, where the focus is on making a entirely new data set where challenging kind of images are there, and putting all the good image detection algorithms or models into action and trying to see that how it performs against this new data set. This new data set, by the way, is called the NAO, it's for Natural Adversarial Objects. That is the one which is proposed in this paper. Now, just to give you a brief summary, as I said, that if my training is as good as the data on which I was being trained, it has been seen that in the NAO data set which was created, most of the models which achieved actually very good performances, it did quite poorly. So in this particular paper, what is more discussed is how this particular NAO dataset was created and why the creators of the dataset believes that this is probably a much more robust method check for adversarial attacks on models. So with this, let me come to the first part, that what is an adversarial object in the first place? Right? I mean, I'm sure that this particular term is new to anyone. In the case of a adversarial object, here we are talking of out of distribution dataset objects. So this examples or these models are specifically created so that the inputs can confuse the model, so that the target model produces erroneous outputs. For example, the image which is there on the screen right now. Just I would like to take a poll Anyone, any idea what exactly this image is about? The image that you see on the screen right now. Anyone, any idea what this image is about? Wild guess, anyone? No? Okay. This image is that of the sphere. As you can understand that this is probably not a very commonly encountered object, but again, that is it, the image of the. And you know what popular machine learning models which detects image, they have identified this image, picture as, it has been identified as the picture of a jellyfish. You can understand, sphere and jellyfish, they are wide apart, but that's how the classification was made. And this is a adversarial object. Now the next question comes is that, should we be very much concerned about adversarial object? Because see, I mean the adversarial object, if it comes in, it can't tamper with the model. See, I should only be worried if there is some information, some data which can adversely tamper my model, tamper my detection process. So in that way, adversarial object is nothing but some kind of a training data which is there. How can it adversely affect my model? So let's talk about the challenge that we are having right now. See, in the case where we are talking of the deep neural network model getting fooled by some randomness, by some data which it has not encountered, then we'll say that this particular threat is a very narrow. Why? Because there are always cases which may be a fraudster or someone who wants to trick the system can fabricate. We have so many models these days. GAN models are there, right? The enforcement models are there, and using that, we can actually create those deepfakes as they're saying. So these threats, as they're saying it's a narrow threat. Why? Because this kind of a manipulations are threat, but inherently in the model which we have created, these examples doesn't have the capability to access the model. The trained layer of the models, the freezed weights which are there, this probably can't affect that. But the problem is that there are some real life objects whereby it creates issue the deep neural network models. For the real life objects also, which are true items, these are not out of boundaries or out of scope images. These are very much in scope images. Here also, the problem is that traditional models are not able to detect this adversarial images. What happens is, even if a detection is there, the detection is there with a very, very low probability. Let's say in the case where we are trying to overfit all the models which are there. Still, some changes in the model, things like the backdrop has changed, the background has changed. There are overlapping objects. When even the best trained image recognition algorithms, they continue making on errors. And when these errors are being made, what happens is the features which were not that much robust. All of you, I think, or most of you already know that in an image recognition algorithm or system, what happens is there are some principal features which gets identified. And based on this principal features only, the images gets annotated. But here in particular cases, what happens is the non-robust features, the ones which get exposed. So that's the potential challenge that we have. So talking about the NAO data set, which has been created, which is discussed as part of this paper. So what is this NAO object detection paper, right? So here, the objective is not to probably get the best model, as I said, but to look into the commonly used image detection algorithms and record the worst performance that they can have. And by the way, this worst performance is also benchmarked against a commonly known and popular data set for image recognition, which comes from Microsoft Contextual Database, which is there. It's called the MSCOCO dataset. In this MSCOCO dataset, what it has been found out is that whenever we are talking of the NAO images, adversarial images, what happens is that typically when a comparison was made as to why, even though the image was there in the MSCOCO, how it ended up being a adversarial object. What was found was that this particular images exist in something which is quote unquote the blind spot of the MSCOCO dataset. So these are probably the points in the dataset, the features in the dataset, which most of the models, I'm not saying all the models, but most of the models, they actually had omitted. And that's the reason why these datasets, even though they are valid images, data, they ends up being marked as adversarial objects. You can think of this, the analogy in this way, that whenever we are talking of outliers in a data set, right? We are talking of numerical data. Outliers are there in the data set, which you can measure by statistical methods. Sometimes you can have real outliers, or sometimes you can have probably fabricated outliers. So fabricated outliers are very easy to detect. You can just check for the mathematical precision that whether they're out of the bounds or not, you can just get them removed. But for real outliers, if you're removing the real outliers, then probably you are not doing a justice to your machine learning or deep learning models. That is the same analogy which I'll be using out here. So here you can think of these NAO objects being some kind of outliers. Outliers in the sense that whatever are the features or the parameters which are there in the objects, principal objects which are there in those images, that is something which they are not able to detect or identify. But having said that, these are actually real images or true images. Just because the feature was not very prominent, they ended up in the blind spot. But in that way, you can't just nullify these images. So the way in which the NAO dataset was created was first an analysis was made with the MSCOCO dataset. It was found out that it only has some limited object categories. Only about 80 categories was there in the MSCOCO dataset. While the open ImageNet, which was being used, so there about 600 categories were there. Right? So this images from the open images were being used along with the annotations from the MSCOCO in order to create this new NAO dataset. So let me show you some examples of the NAO dataset. On the screen, you're right now having 4 images. The one on the top left side of the screen, actually it's a box squirrel. But most of the algorithms, it ended up detecting this as a sea lion. If you see the next image, as you can see, the image was that of a dragonfly. But most of the image detection algorithm termed it as some kind of a manhole cover. If you're coming to the third one, this is the one which I had described at the very beginning. This is the image of the photosphere, while most of the algorithms are saying that it's a picture of a jellyfish. The last one, though it is not a jigsaw puzzle, but most of the images said that it is a jigsaw puzzle. right? Now, how this particular data set is created, right? As you can understand that none of the images, they are fabricated. Each of the images, they have been carefully curated. And these curated images are curated in such a way that they actually use the best image recognition algorithm. How it is created? First thing was to compare the predictions of the various off-the-shelf image recognition algorithms on all these images. And by the way, here we are considering data set which is already annotated. And then from all the images, so we have these several algorithms which are there. The images which were misclassified, high confidence of false positives, those were the ones which were separated out. Cases where the annotations were there, but the images in cases they were misclassified, we filter that out. After the filtering process is done, some of the images where the object was not very clear, image was not very sharp, there were blurry objects, so those were removed. And then finally a re-annotation process was run to annotate the picture again. That is how, in a nutshell, the NAO data set is created. I'll show you the steps as I was saying, right? First, as I said, take the existing algorithms which are there, run these existing algorithms against data set where the objects you already have annotated objects, find out the cases where there were a lot of misclassifications by most of the algorithms. Maybe not all, but most of the algorithms, they misclassified. From this misclassified data set, filter out the cases where there were blurry images. And then finally, what you do is that you re-annotate them with this MS-UCO data set. That was precisely what was done in order to generate the particular images, right? Now, after this particular part, right, I'll tell you about some of the limitations of this MS-UCO data set. See, this MS-UCO data set, it has right now at this point in time, it is considered as one of the most prominent data set when it comes to image recognition. So again, I mean, it's a common object in context. That's what the MS-UCO data set does. There are several limitations of the MS-UCO data set, right? As I said in the very beginning, that though it contains more than 100,000 images, right, of which close to about 5,000 images are there in the validation data set. But yet the images are only categorized in 80 object classes. So common kind of annotations like that of animals, that of common day-to-day objects like your car, clock, those are the things which are basically figured out. But some of the popular categories, things like even fish, is not there as the category in the MS-UCO dataset, right? So that is some of the limitations which is there, resulting which what has happened is that the annotation or the training which is being done on the MS-UCO dataset, sometimes it is not proper. That's why the images which was being used for this NAO were sourced from this open images BC dataset that had 600 different image categories. I'll just show you the results from the annotation process, right? So as you can see, the annotation process does two things. First, it looks at the image and tries to look into the prominent objects in the image. Next, it creates some kind of a square boxes around the images. And for each of these square boxes, what it tries to do is it tries to figure out that what exactly is the object which is embedded in the square box. So basically, if you see the process, it's a two-stage process. One is the classification stage, right? In the classification stage, what happens is that the annotator, it tries to identify that whether the object which is described in the bounding box, is it as per the ground truth which is defined annotated in the OPG images, or is it something else? Once the first part is done, the next part is the bounding box stage, where, as I said, as you can see in the picture, most of the objects are being surrounded by some bounding box. And then based on this, an inference is tried to be made as to what exactly the image is talking about. Right? Let's move ahead. Now, this is some of the things which came out from the results. Right? So here, in this examples, in this picture which I'm showing you, the ground truth is already there in the distribution. Let's look at the first image, the one which is on the top left. The prediction here is that of an airplane, but the actual image is that of a boat. Right? The second case, as you can see, it's some kind of a flower from a potted plant, but the prediction is that of a banana. The one on the top right, the prediction is that of a book, but actually it's a cell phone. If you see the bottom row, the picture in the middle, so here is a beautiful lady who's swimming under waters. Here the prediction is bear, but actually it's a person. And the last one, top right, the prediction is that of a fire hydrant. Yes, we can agree that it does have, if I just show you some parts of it, let me use my pen. Yeah, this particular part, right? We know that it is indeed there in some fire hydrants. The other part in red, yeah, it's there in fire hydrants. But again, who have seen fire hydrants with a pair of eyes and a smiley? Yet this is being termed as the fire hydrant. And by the way, in all these cases, the ground truth was there in the data distribution. Come to the case then where the ground truth was completely out of the distribution. Here you see the first one. The prediction is that of an airplane, but actually is something else. It's a probably some kind of a architecture of a rhino head. The second one, prediction is that of an apple. Actual some unknown flower. In the third case, the prediction is that of a baseball bat. Actually, it is some form of a hammer. So as you can understand that all these images, they are actually real images. They are not fabricated, they are not created, yet it is very difficult for most of the machine learning algorithms to detect what they are actually talking about. As you can see, the bottom row, the one on the left, the prediction is that of a bird, but you can actually see it's a whale which is there. So these are some of the ways in which the data set was created. You can understand it's very interesting that how the data set was created, right? Next, let me come to the part, the results. MSCOCO, that data set, you can see that the faster RCLN of 2015, you can see the mean average precision, right? So you see on the MSCOCO, and if you see on the adversarial objects, the precision is much less. And by the way, this result of having a lower precision is not only across one or two algorithms. Consistently, the precision is lower across the different algorithms which are there. So which indeed probably goes on proving that this NAO data set is probably a much more challenging data set for most of the existing state-of-the-art object detection algorithm to have good results, right? So again, as you can see, constantly over the year, except barring I think 2018, in most of the other years, the results of the state-of-the-art algorithms was most of the cases better than the previous years, right? So again, you see 2019, right? Then 2000, all these three efficient D2, D4, D7, most of the cases they have outperformed the previous algorithms. But you see the case of the NAO. For the NAO object detection dataset, in most of the cases, the performances for these different algorithms, that was not consistent. One thing which is true is that all of them performed quite worse compared to the MSCOCO dataset when it came to the NAO dataset. The other case is that even with better algorithms, the performance of the detection of the NAO dataset, that also didn't change much. It's not that there is some kind of a pattern which you can see. Now, what were the reasons for the common failures in NAO detection? Once you have seen that constantly it is failing to detect the NAO, what were the reasons of failure? One of the reasons of failure, which is again perfectly attributed to the fact, and again we humans also, we can make this kind of mistakes if probably the image is not proper or it's blurred, that the image which is presented, it is superficially very much similar to the ground truth. For example, clocks and coins, if you see it from a distant, maybe in some of the cases both of them they will look the same. When you take a closer look, maybe they will look different. Shark and aeroplane, which most of these models they are constantly making this particular error. It's different, but again they are mixing and matching it up. Other places where also it the objects they were grossly misclassified was with pachyderm animals, right? Animals which are thick-skinned animals like rhinoceros, elephants. This kind of cases, what it did was it took the pachyderm or the skin texture as the principal feature, whereas as you know that a rhinoceros doesn't have a trunk, whereas the elephant does have a trunk, but still there were a lot of misclassifications which happened. Like, and the elephants were classified as rhinos in most of the cases in the NAO data set. Right? So again, some of the common failures picture is where I'm showing that to you. In most of the cases, see the first one, prediction was umbrella, where moth was out of distribution. Bird, it is predicted, where fish was out of distribution. Again, when I'm saying this out of distribution, that is with response to the MSCOCO dataset on which the annotation was done. Right? Next, what we are looking at is what will happen. The background of the image is replaced. Because this model is getting confused, if the background of the image gets replaced, that the performance is better, the change in probability of their identification is far better. As you can see in the results section, right? The image which I have shown you. Even in the case of this background cues. So what has been done is some of these images, they have been replaced with the frequently appearing background elements so that the classes can be better understood. What happens has been seen that NAO objects which were found out, they have a common tendency to focus too much of the information which is within the predicting bounding box. Whatever is not with the bounding boxes, and there in some of the cases, the main component lies. The model is not making any focus out there. Okay? So if you see the average change in probability of the objects that the backgrounds are replaced. So again, if you see the legend, you'll find that the orange ones, represents the NAO cases, while the blue ones represent the MSCOCO. So again, the small change in probability, as you see, indicates that the detection of the model did not make any use of the background to classify the object. So that was also another cases that we saw where why this model was failing. Now there was a very interesting paper which came out from Google in 2017, which is called the integrated gradient analysis. So what it tries to find out in the integrated gradient analysis, the method, what it tries to find out is the proportion of the integrated output within the boundary blocks. Right? So this is mainly being used to understand the context of the picture, and that will help in the classification part. So again, as you can see from the results, right, it's very evident that even after integrated gradient analysis was used for in some of the models for detection. But again, it clearly shows that the detection model did not make use of any background information, or in most of the cases, the background information was not taken into account when the image classification was made. I'm coming to the final bit of the presentation, right? Again, this is the where the integrated gradient analysis, as you can see, that the background image part was not really that much taken into account. And finally, the scores of the MSCOCO versus the NAO dataset. If you see the mean average precision of these algorithms, in most of the cases, the mean average precision, right? Not in most of the cases, I take back. In all the cases, the mean average precision of the MSCOCO is significantly more than that of the NAO algorithm. Right? See, in the case where the out of distribution objects they are being classified, here you can see that the MAP of the MSCOCO vis-a-vis the MAP of the NAO, they are in some way comparable. But again, for the cases which were completely out of distribution, so there you can see that the MAP is significantly lower in the NAO dataset. Right? Okay, so that brings me to the last part of the discussion, and right now I'm open for any questions from your part. Yeah, any questions from anyone? I'll be happy to answer. No questions? Okay, I understand, quite late in the day for some of you, but again, just rounding up, just to give you the basic gist. As I said, I think there's some question in the chat. Okay, thanks, Henry. No question. I'll just go back to what I started off with. Most of your machine learning algorithms, deep learning algorithms, they are as good as the data set on which they have been trained. Right? Now, this particular paper, what it does is talks about a new data set, the NAO data set, adversarial object data set, where what is happening is that the natural tendency or the natural way in which objects are getting classified in some way or the other, that is being some way or the other it is blurred, or again it has been tricked into thinking that it is some other object. Now, outcome from this be obviously look into the existing algorithms, try to find out that why they have been making constantly mistakes on these NAO algorithms. I think I've already told some of the reasons where they're making the mistakes. Right? They are not taking the background information into account. The boxes which are being marked in it, some of the regular objects there, being able to identify, not the out of boundary objects. We can do that maybe in the next round of iteration of the common image detection algorithm. Probably they will run much better, or will be able to do a good job on the NAO data set as well. Okay, thank you everyone for being in the session. I appreciate your time. So if there is no further question from anyone, I would like to end this discussion. Sam is there? No, I think
okay,
he's
thanks.
not there.
Yeah, thank you, Surav.
Okay. Thank you. Thanks,
Bye.
Sergey. Thanks, Sadiq. Yeah, Henry, Logan, Lorenzo, Mikalo. Thanks, everyone. Have a nice day. Bye-bye.
Yeah, bye-bye.